Hi. We know for a fact that in software engineering, when we hit a wall with vertical scaling, you can only add so much RAM or CPU to one machine before it becomes cost prohibitive or physically impossible. Distributed systems are the industry's answer to this wall. But moving from one machine to many isn't a free lunch, it exchanges hardware simplicity for complex coordination. A distributed system is a set of spatially separated nodes that communicate via message passing to achieve a common goal. We transition from monolithic to distributed for two technical reasons. One is horizontal scalability, that is overcoming the vertical limits of single node CPU or RAM. And the second one is redundant availability, which means we are eliminating the single point of failure. However, once you move from local function calls to network based message passing, your failure modes change. On one machine, a process is either up or down, and in a distributed system, a node can be semi-alive. That is, the CPU is running, but the network cable is cut. This uncertainty introduces three fundamental obstacles. Every distributed problem fits into these three buckets. One is communication, that is, network is an unreliable medium, and we have to design for packet loss, jitter, and varying latency. Second one is coordination. Since we lack a global shared clock, how do nodes agree on a value or elect a leader? The third is state. How do we manage data consistency when records are physically replicated across different disks and data centers? Identifying these obstacles is step one. Step two is recognizing that you cannot solve all of them perfectly at the same time. There is a mathematical boundary to what a system can actually guarantee during a failure, and we define that boundary using the CAP theorem. CAP states that in the event of network partition, a system must choose between consistency or availability. So we have CP systems where if a node loses connection to the majority, it shuts down reads or writes to prevent data corruption. And then we have AP systems, that is, the node continues to serve traffic using its local data, accepting that it might be serving stale or outdated information. So CAP tells us what we can't have, but it does not tell us how to build what we can have. If you decide your system can tolerate some inconsistency to stay available, you need to define the exact depth of that inconsistency. So this leads us to consistency models. We choose models based on the required latency and business risk. We have strong consistency that focuses on linearizability, that is, every read returns the result of this most recent write, and this requires synchronous coordination, which increases latency. Then we have eventual consistency, where we have high throughput and low latency. The system guarantees that if updates stop, all nodes will eventually converge on the same value. Then we have read after write, where a specific guarantee ensuring a user always sees their own updates immediately, preventing any missing update or a UI bug. So consistency model is a policy. To enforce that policy in the real world, you need an architectural pattern to physically move the data between nodes, and this is where replication topologies come into play. So replication is the mechanism for achieving our consistency goals. So we have leader follower approach, we have synchronous approach, we have asynchronous approach. So basically leader follower approach is where we ensure an ordered sequence of events. All writes go to a single leader. And in synchronous, here the leader waits for an quorum or all follows to acknowledge before confirming the right to the client. This is how you implement strong consistency. And then we have asynchronous, where the leader confirms the right immediately. This maximizes speed but risks data loss if the leader fails before the followers are updated. Replication handles how data is stored and synced. So, understanding these primitives, the trade offs between latency, consistency, and replication, is the foundation of system design.